Hi everyone, for today's lecture we will talk about our term project. Firstly, the buck boost converter design. Here are the requirements and specifications. From what we learned before, we can easily get this circuit for buck boost converter. And from this circuit, we need several parameters to be calculated, which is duty ratio, inductor, capacitor, and resistance load. How to calculate those parameters? Using these equations in these slides, we got D equals to 0.4, L we choose which is equals to 5, and capacitor we choose 8 wafer. Using this simulation, we put the inductor value here, capacitor, and resistance load. And we also need to set this the frequency equals to the crossover frequency. This is the PWM for control the circuit. Okay, we see the result. Vout is equals to minus 40, which is as shown the specification. And the inductor current is equals to around 8.3, which is equals to input current minus output current. If you zoom in, you can see the result like this, which looks good. Okay, then we will go to part B, the boost converter with a feedback controller. The feedback controller in part B is just a current feedback controller, and in part C we will talk more about both inductor, both current feedback controller and voltage feedback controller. So let's start talking about control loop. Here we need three transfer function: controller, PWM, and power stage. There is the desired Vout, and using this with this output, compare these two values, we know how to calculate this circuit. Okay, let's go to step 1, is PWM design. We set VR equals to 1, and then we got GPWM equals to 1. Then is the power stage design. From this equation we find in the notebook, we got duty ratio equals to 0.6, and we choose inductor equals to 40 Wh. And so this equation we can also find it from notebook chapter 4. So it is for boost converter. So we got power stage transfer function from here. Put this in MATLAB, we find the body plot. We just show here. You can see that when the frequency is around 5 kilo-rad per second, we got the magnitude is around 88.1, and the phase margin shown here. Here is the value. We can calculate it from the body plot. Okay, for step 3, the controller. To control the current control loop, we have to find Kc, omega z, omega p. How to calculate this value? As the phase margin is around 60, the desired, we got the boost. The phi boost is here. And calculate parameters. We set KFB equals to 0.2. And with all those parameters that need to be calculated, we finally get the current controller transfer function. We also put it in MATLAB. You can see the phase margin here is 90 degrees, but the desired one is around 60 degrees. It's a little bit larger. And then using this equation, we got GL, which is the closed loop circuit transfer function here, and also put it in MATLAB, got the body plot. Then we will talk about op-amp design. Here is the circuit that we will put it in the simulation. So we choose R1 equals to 100 kilo, and using the equation from chapter 4, we can easily get this value and then put this is exactly the same with here. Let's start our simulation. So we put L1 equals the value here, and then the current here. Oh, we also need, this is ESR. We can find this cheat sheet table from the Google website. You can find it here, that this value has to be some connection with the capacitor. So you can see the current control loop is here, which will control the circuit of here. And we set all these values, and the KFB is here. So from the requirement, we have to change the load from here. There are two loads, which have these three values, divided by 2, multiplied by 2. But the output voltage is almost the same from the result we can see from here. That is our design for part B. Okay, let's move to part C. Part C, as we talked before, the difference between part C and part B is that it added a voltage control loop, and here we will mainly talk about the voltage control loop, as the current control loop we already talked about in part B. That is exactly the same with part C. You can just easily follow those steps. Okay, here. For the current control loop, which you can see is exactly the same. We got the inductor controller transfer frequency from here. Okay, then let's move to voltage loop design. We have this equation from notebook, and here are KV, omega CV we have to calculate. So using the equation from chapter 6, we can calculate here. As you can see, VD2 peak is the capacitor value, and IL2 is around, have some connection with inductor current. You can see from here. So we got omega CV and KV. Put it inside, we got the GVS, which is voltage control transfer function. Okay, let's start our simulation. Here we need a transfer because the original value is 120. So here we need to set is 110. There are two loops, as you can see from here. This loop is control the current, and we using this loop to control the voltage. These are the parameters. For PI, we need to try so many times, but there are also some equations that you can use. So we need to put the parameters that we calculated for the inductor and capacitor and this load, put it inside. As we can see, here are two inductors, which used to make the ripple smaller. Here is the result. The output voltage is around 30. Here are small ripples. The input voltage and input current is shown here. I think there are some which is not very good for the input current. Okay, that's it. Thank you for listening.